right, I am re-recording the first lesson in stoichiometry because the audio didn't work, and now I've got a microphone, so hopefully that will work. I'm going to be using examples from your homework assignment on stoichiometry. We'll start with the first one. Calculate the number of moles of potassium chlorite, KClO3, that must decompose to produce potassium chloride and oxygen. All right, so KCl plus O2. Well, before we start on these, let's expand our world perspective on what makes reactants and products and the stoichiometry flowchart per se. All right, so here let's increase our stoichiometry flowchart. All right, so our stoichiometry flowchart. In the past, we said we could go from moles of something. In this case, we'll call it moles of A. We could go from moles of A. You know what? I'm using a darker pencil here so y'all can see this better. Moles of A, we can go from moles of A to grams of A, or to number of particles of A. So we can start this direction, go grams, or we can go number of pieces. And there's connections here. This is a molar mass. That gets us from grams to moles of A, and this is Avogadro's number. That gets us from particles to moles. Well, now we're adding a component to our stoichiometry flowchart. We're going from moles of A to moles of B, and this is called the mole-bridge ratio. And the mole-bridge ratio comes from the balanced equation. Coefficients that are in front of the balanced equation. I'm going to give you some examples of that in just a minute. Well, once you get to moles of B, you can use that information to get to the rest of the problem, which in this case could be grams of B, using once again the molar mass to get there, or to number of pieces of B using Avogadro's number. All right, so there's our model. There's our stoichiometry flowchart as we're going to use it. Now let's start looking at some of the problems from that homework assignment. I believe it's homework 12. I'm going to do the first 4 problems for you to get you started. All right, so if we look at homework 12, it says, let's go look at the problem again real quick. I'll pull this up. Problem says, calculate the number of moles of potassium chloride. So we want to know how many moles of this stuff that must decompose to produce potassium chloride and 1.8 moles of oxygen gas. All right, physics taught me how to draw pictures, and I translate that into my work in chemistry now because it seems to help me keep track of things. It also seems to help students keep track of things. So this was the problem. They want to know how many moles of this stuff, this potassium chloride, must decompose. Remember, decomposition reaction. You're starting with something that's bigger. You're going to things that are smaller. And what we want to make is 1.8 moles of this oxygen gas. I'm assuming this is probably going to be a solid also. Well, let's double check and see if this is balanced. I don't think it is. We got 1 Cl, 1 Cl, 1 K, 1 K. We got 3 O's there and 2 O's there. And I always tell students when you've got uneven numbers on both sides, look at the lowest whole number ratio between 3 and 2. In this case, that would be 6. So we want to get 6 oxygens on each side. So I'm going to put a coefficient of 3 there and a coefficient of 2 there. And now that fixes the oxygen, but it messes up the K and the Cl. But we can easily fix that just putting a 2 in front of the K and the Cl. Now our equation follows the law of conservation of matter, which says matter can't be created or destroyed. It's balanced. So now in the problem, we're going to start with our known quantity. In this case, 1.8 moles of oxygen gas. And make sure in these kinds of calculations that you always put the unit as well as the substance on each of your numerical quantities, and that will decrease your errors by 90%. So we're starting with 1 mole. We want to get to moles of KClO3. So if we look at our stoichiometry flowchart, this is actually a fairly short journey. We're just going from moles of one thing to moles of another, which involves the mole-bridge ratio, this balanced equation idea. So if we take our 1.8 moles of O2, I'm going to set up a conversion factor. I'm going to put my units and substance on the bottom of the first conversion factor, which in this case is moles of O2. I want to go to my second substance. In this case, here's where I was starting on, my stoichiometry flowchart. I'm going to moles of the second substance. So I'm going to put moles on the top of the conversion factor, and the second substance in this case is the KClO3. Now that's the hard part in setting up this particular equation. And now I have to get the coefficients from the balanced chemical equation. Turns out the coefficient in front of O2 is 3, so I put the 3 there. The coefficient in front of KClO3 is 2. So now with my calculator, I would simply punch in 1.8 times, and now we're going to use our parentheses buttons. This is a new one we haven't used yet. You want to look on your calculator for 2 buttons that look like this, open parentheses and close parentheses. And what you're going to write, you're going to type in your calculators, you're going to put in 1.8 times, then you hit open parentheses, 2 divided by 3, close parentheses, and the answer you should get is 1.2. And since moles of oxygen canceled, our units in substance that we're going to come through in the equation is moles of KClO3. So that's the simplest of the mole-to-mole conversions in this particular homework assignment. Let's look at number 2. Look at number 2. Number 2 says we're doing a single replacement reaction, all right? Single replacement with magnesium metal, Mg, as a solid, and hydrochloric acid plus HCl to produce magnesium chloride, MgCl, and hydrogen gas, which you should know at this point the formula is H2. How many moles of hydrochloric acid, so that's the question, how many moles are needed to completely react with 2.43 grams of magnesium? 2.43 grams. All right, let me show you the picture I drew based on reading that problem. Magnesium is a reactant, hydrochloric in aqueous solution is reactant. I had to write the formula for magnesium chloride. If I look at the periodic table, magnesium's ionic charge is +2, chlorine's -1, so the appropriate nomenclature for magnesium chloride is that in aqueous solution, and H2 is in fact a gas. Now we have to balance it because the coefficients are actually really important to these equations. Well, the H's need to be balanced as well as the Cl, so I think we can balance everything by putting a 2 in front of the HCl. Now we're going to start with our known quantity, in this case 2.43 grams of magnesium solid, and we have to look at our stoichiometric flow chart. So in this case now we're starting at grams, right? Here's where we're starting is grams, and we're going to moles. So if we look at our stoichiometry flow chart, I'm starting at grams, and I got to get to moles of another thing. So that's actually 2 steps in the flow chart. So this time I'm going to have 2 conversion factors because I have to have 1 step to get me from here to here and another step to get me to moles of B. So now we go ahead with the problem. I'm going to take the units in substance. I'm going to transfer those to the bottom of my first conversion factor. Based on my stoichiometry flow chart, I'm going from grams of magnesium to moles of magnesium. So moles of Mg. Now put all the units in substance in before you put any numbers, and that will decrease your error. I'm going to take moles of Mg, I'm going to put it on the bottom of my second conversion factor because here's where I am now. Now I'm going to moles of the second substance using my mole-bridge ratio, and in this case my second substance is moles of HCl. Moles to anything else, 1 always is the coefficient in front of moles. If I look at the periodic table, let's see what the molar mass of magnesium is. Let's check that out real quick. Remember, whenever you see molar masses, you got to look at the periodic table for AMUs or grams per mole. Here we go. Here's the periodic table I want. So now we're looking for the molar mass of magnesium. Apparently that is 24.3 according to the periodic table. So I'm going to put that in to my equation here. 24.3, and that, remember, comes from the periodic table. Now our mole-to-mole bridge ratio, those coefficients come from the balanced equation. In this case, HCl has a coefficient of 2, Mg has a coefficient of 1. So now in your calculator, you punch in 2.43 divided by 24.3 times 2, and whatever your answer is, you want to have 3 sig figs, and our units are moles of HCl. All right, let's do the third problem. Third problem. Now we're talking about a different substance. In this case, ethane. Ethane is C2H6. Apparently, ethane reacts with oxygen gas. In this case, we know oxygen gas is O2 to produce carbon dioxide gas and water vapor. What mass of oxygen gas, and we want to know how many grams of oxygen gas are required to react with 2.2 moles of ethane. So 2.20 moles of this stuff. All right. So here's my picture. I'm going to share my picture with you. All right. Here's my picture of the reaction. Here's my ethane, C2H6 with oxygen, makes CO2 and H2O. We're going to need to balance this, and since I've already done this once, I know that there's a 2 that goes there, so we probably need a 4 there then. And 2 times 6 is 12 hydrogens, so we need to put a 6 there to make 12 hydrogens there. Now we've got 4 times 2 is 8 oxygen there, plus 6 more, 8, 9, 10, 11, 12, 13, 14 oxygen on this side. I've only got 2, so I can put a 7 there, and now my equation is balanced. All right. If we're starting with 2.20 moles of this, we need to know how many grams of this we need. So we start with our starting quantity, 2.20 moles of C2H6. Now if I look at my stoichiometry flow chart, once again, I'm starting at moles, and I need to get to grams. So it is also a 1-2 step conversion. So I want to put 2 conversion factors. I'm going to take my units in substance from my first one. I'm going to put it on the bottom, moles of C2H6. And using my stoichiometry flow chart on moles here, I don't want to go backwards. I want to go forward, so I'm going to go moles of the second substance. So moles of the second substance, in this case the O2, is going to go on top. Then I'm going to take moles of O2, I'm going to put it on the bottom. And according to stoichiometry flow chart, if I go moles of O2, I got to go to grams of O2. So grams of O2 on the top. Now, this ratio comes from our balanced equation. O2, coefficient happens to be 7. C2H6, coefficient is 2. Moles of anything to grams. Moles always has a coefficient of 1. This is tricky. A lot of students want to put 16, but you got to remember that's a 2, so that's 32 grams. So in your calculator now, you'd punch in 2.20 times, open parentheses, 7 divided by 2, close parentheses, enter, times 32, enter, and that should give you your answer, and you should report to 3 sig figs with grams of O2 as your final units in substance. All right, one more problem, and then you guys should be able to do this on your own. All right, last problem says, determine the mass of sodium nitrate produced, and here's our equation. We got nickel nitrate plus sodium hydroxide gives us nickel hydroxide plus sodium nitrate. All right, so we want to know the mass of sodium nitrate produced. So we know that's a product, so we need to know how many grams of that we make when 0.73 grams of the nickel nitrate, so 0.73 grams with sodium hydroxide reacts. All right, let's look at the picture I drew based on that particular problem. Here's the equation that was given to you in the problem. They want to know how many grams of this stuff can be made if we start with 0.73 grams of the nickel nitrate. So once again, 0.73 grams of the nickel nitrate we're going to start with. And if we consult our stoichiometry flow chart, we're starting at grams of one thing, and we need to get to grams of another. So this is a big honking problem. Grams to grams. So that involves 1, 2, 3 steps in our stoichiometry flow chart. So I need 1, 2, 3 conversion factors. Once again, grams of nickel nitrate on the bottom. So if they cancel, using my stoichiometry flow chart, I'm starting at grams here. I want to go to moles of the same thing. So on the top of my first conversion factor, I'm going to put moles of nickel nitrate. I'll take my moles of nickel nitrate, I'm going to put on the bottom so it cancels. Now I'm here in my stoichiometry flow chart. I want to go from moles of nickel nitrate to moles of the second thing. In this case, NaNO3. So moles of NaNO3. NO3. I'm going to move that to the bottom of my last conversion factor. Using my stoichiometry flowchart on here, I want to go to grams of NaNO3, grams of NaNO3. All right, once you've put in all the units in substance and all your conversion factors, then go back and put numbers in, and that will eliminate a whole lot of errors. Moles to anything else, 1 always goes in front of moles, 1 always goes in front of moles. This, the coefficients come from the balanced equation. NaNO3 has a coefficient of 2, and INO3 has a coefficient of 1. Figure out what the molar mass is here. That number goes in that spot. Molar mass here. That number goes in that spot. You should be able to do the math at this point. All right, that gives you 4 solid problems to start with and work. And I've already recorded the second stoichiometry video, so hopefully this will help with the audio portion that was difficult to hear from the first one.